Our next speaker, I had the privilege of meeting and introducing at another conference called GrimCon, almost a year ago, maybe. I don't know how long this was. Time is difficult to keep track of nowadays, but it is Mike Goldterry. So Mike has been pretty active in security. He has a very cool intro to security story that he did at GrimCon. I don't know if he's going to share it here. I think now you have to because I mentioned it. All right, cool. So he's been around doing and being a hacker for a long time. This talk is going to be that one talk that's going to mention SolarWinds, which we haven't heard that much, but it's not going to be so much SolarWinds and more about DLL hijacking, which we all love, right? Because it's one of those things that's like an opportunity that occurs when we are looking at endpoints and have the ability to inject and or escalate privileges or gain persistence. It's like that one that does multiple techniques at the same time. So we love it. Mike is a security engineer at Gatsby, which he hasn't been there that long. So congrats. I think I officially can tell you congrats on that new gig.
Thank you.
Yeah, go ahead and take it away. And sorry, now you have to do that intro that we love.
All right. Thank you, George. Thank you, Eric. I am excited to be here today at the SANS Purple Team Summit. And I was fortunate to be able to speak at the community-driven Purple Team Summit last November. And I said it in the fall, but I'm going to say it again. Coming from an offensive security perspective, purple teaming is, in my opinion, one of the most exciting industry trends in recent years. So today, we are looking at what's become one of the hot button topics of 2021. No, not ransomware, supply chain attacks. So supply chain attacks are one of the most difficult vectors to defend against, in my opinion, at least, as you inadvertently are providing an adversary access to your environment on a red carpet. But just because things are difficult to defend against doesn't mean they are impossible. Regardless of the initial vector of compromise, attackers tend to follow the same tactics, techniques, and procedures, TTPs, to infiltrate networks. So in this presentation today, I'll be providing a methodology of how to simulate supply chain attacks in a realistic manner using an age-old Windows trick, DLL hijacking. We'll be both looking at simulating the attack and how to build up detections to defend against such an attack. A quick background about who I am. I'm Mike Goldterry, and I've been in software and cybersecurity for more than 2 decades, wearing both business and technical hats throughout my whole career, usually both at the same time. About a month ago, as George mentioned, I took on a new role as the staff security engineer at Gatsby. So who and what is Gatsby? They're so nice to give me the day to speak with you instead of working in my regular role. Gatsby is a web and technology stack that enables developers to build fast, secure, scalable websites. We develop both the open source Jamstack Gatsby framework, and we offer the Gatsby Cloud, which is a cloud to swiftly build, deploy, and preview websites. And so far, I can't say enough good things about working at Gatsby. It's been awesome to be in the position to secure a disruptive web and cloud technology stack at a really cool company. So check us out. We're going to be doing a lot of really cool things in security soon. In addition to my role at Gatsby, I'm actually on the part-time faculty at the University of Pittsburgh School of Computing and Information. And specifically, I teach for a program called the Professional Institute. For the Professional Institute, I developed and teach 2 courses for the program, the Offensive Boot Camps 1 and 2. These courses teach students vulnerability analysis and penetration testing. And prior to Gatsby, I spent 15 years as an entrepreneur where I ran a software design and development firm. I was the principal consultant of an offensive security firm, and I founded a children's technology company built on Linux and open source software technologies. And because George asked, I'm going to give 1 second here or 10 seconds on my origin story. I knew I was a hacker because when I was a kid, I decided to password protect all my floppy disks on my Apple II computer, and I found those disks 20 years later, and they were password protected, and I had to guess what the password was. And the password was, of course, Ninja. So I got my kind of ninja start as a hacker at a very ripe young age there with my Apple II. All right, so enough fun. Let's get the real content underway here. First off, what is a supply chain attack? Simply put, it's an attack that's conducted through a breached vendor, a trusted third-party system or software. You install a valid piece of software on your network that has been inadvertently backdoored by an adversary, initiating a breach. We should also define what a supply chain attack is not, at least for the purposes of this talk, because that's the fun part about InfoSec, right? No one can agree on any definitions for any terms. But what a supply chain attack is not, at least for the purposes of this talk, is when an attacker uses a vulnerability in a piece of software to gain access to a system or a network. So you might be asking, isn't that the same thing? No. In a supply chain attack, the adversary introduces the flaw into a piece of software with the goal of gaining access to victim systems. In the other scenario, an attacker just abuses flaws found in software to gain access to victim systems, which is pretty much what happens in every other type of attack scenario. So in my opinion, a supply chain attack is one where an adversary has subverted a piece of software that is then installed onto other networks. Can anyone name a vendor who might have been in the news for a supply chain breach? That's right, CodeCov. But if you answered SolarWinds, yeah, that one was pretty bad too. So in the case of CodeCov, which is a little more recent, attackers modified their bash uploader product, which is inserted into the CI/CD pipelines of many companies around the world, with a goal of stealing credentials and private code repositories. At least 29,000 companies have been affected by that breach. For SolarWinds, 18,000 customers were affected when they updated a tainted Orion software product update. Although now we know that the actual targets of the SolarWinds sunburst attacks were actually very specific, federal government agencies and big tech companies. So the problem is multi-platform. CodeCov mainly affected Linux. SolarWinds mainly affected Windows. We also have this one. Has anybody ever heard of MageCart? So MageCart, in my opinion, is another great example of a supply chain attack. MageCart, if you haven't heard of it, is a loose-knit group of attackers who compromise third-party JavaScript libraries to steal sensitive data, mostly credit card information, from websites. So supply chain attacks can pretty much affect any platform and any technology stack. And it can pretty much affect any industry, right? A little more than a year ago, a practice management company that provides software used in the dental industry was targeted in the supply chain attack and used to disrupt dental practices with malware, or actually ransomware. Years before, of course, was the famous or infamous CC Cleaner supply chain attack, which compromised millions of machines. Certain industries are more susceptible than others. Industries that rely on a glut of commonly used third-party software have much higher rates of exposure because the entire industry can be targeted by subverting any of those pieces of software. The more valuable the data of the industry or the more potential for disruption, the more attractive the target becomes to an adversary. Now, onto our second topic here. What is DLL hijacking? So DLLs, or dynamic linked libraries, are similar to shared objects in Linux and contain external interfaces used by binary executables running on the operating system. Two methods are available to hijack DLLs. If a user has write access to the path the DLL is located, the file can simply be overwritten, And in some cases, the file just might be missing. Another option is to abuse path precedence, which is what we'll be talking about today. When a Windows binary, also known as a portable executable, attempts to load a DLL that's not been included with an absolute path, the operating system will search for a series of directories for the DLL. The path precedence in Windows is as follows: the directory from which the application is loaded, /Windows System 32, /Windows System, /Windows, the current working directory, directories in the system path environment variable, and directories in the user path environment variable. To perform a DLL hijack, a custom DLL is placed at a location with a higher path precedence than where the actual target DLL resides. Is DLL hijacking a flaw? Sometimes. So if the target DLL location is writable by any user on the system, there may be an opportunity for lateral movement and/or privilege escalation. But most of the time, the DLL precedence paths are locked down and only accessible by the local administrators of that system. For the purposes of the simulation we're going to discuss today, that's okay. We aren't looking to escalate privileges. Rather, we're looking to hijack the execution flow within assigned binary to simulate an attacker compromising the target application in a supply chain incident. So you're probably saying, Mike, that sounds really cool, but how do I do it? I have you covered. I'm going to run through a few slides to give you a quick crash course in DLL hijacking. If you haven't done it before, you can learn now today. If you have but are a bit rusty, this should get you back up to speed. The best tool for the job by far is Procmon, or Process Monitor. So Procmon is a Microsoft sysinternals tool that is essential to DLL hijacking. Procmon monitors the execution of processes and in real time displays file system, registry, and process and thread activity. By default, it will spit out a ton of data. So to be useful, we need to filter it down. 3 filter options are important to find potential DLL hijacks on the system. 1, the process name begins with your application.exe. In our demonstration today, we're going to be picking Google Chrome, so chrome.exe. 2, the result is name not found. And 3, the path ends with DLL. What do these filters do? Well, when applied, they will show every file access that results in a name not found, or rather that the target file is not found, ending in the string .dll, and originating from the binary chrome.exe. Once chrome.exe is started, Procmon will display potential DLLs that are candidates for hijacking. And display it will. This screenshot is an application of output you'll see after executing chrome.exe. The first entry on the list there is /program files x86 Chrome, a Google Chrome application version.dll. The executable is looking for version.dll from the directory that stores chrome.exe, right? The first item in the path precedence. And we can go through this list, and any of these DLLs are hijackable. We're going to be targeting today at crypt-based.dll. But I really want to stress again that none of these are security flaws. For everything on this list, you need administrative access to a place where this file is missing. And that's okay. If you find a writable path, let Google know, get your CVE and get it fixed. And there are definitely still DLL hijacks out there waiting to be found, but maybe not with Chrome. But for our purposes today, these paths will work just fine for our purple team exercise. By subverting execution, by placing a DLL in one of these locations, we'll be able to execute our synthetic malware inside Google Chrome. In essence, we're artificially running a test that simulates, hey, What would happen on my network if Chrome was tainted with malware and shipped out to my whole fleet? Probably be a bad day. But I know I'm picking on Chrome today, right? But try it with other executables. What if Zoom was shipped with a malicious update? What if Slack was? What if something else was, right? We become so dependent, especially in this last year, on a lot of software that really hasn't been run in environments prior to them. So pick a scenario that makes sense to your organization. Now you may ask next, okay, that sounds great, Mike. How do we create this DLL? To generate a DLL to test a hijack, I just recommend using MSF Venom. It's easy and it will work, but there's a big problem. MSF Venom won't likely bypass antivirus without significant modifications. And we want our simulation to be realistic. If an adversary is going out of their way to subvert a piece of software, you can guarantee they're also going to be able to bypass antivirus. So while I recommend using MSF Venom to test a DLL hijack to make sure it's possible, I also recommend spending a little time to create a custom DLL from scratch. If you do this, it's extremely unlikely that it will be caught by antivirus and probably also won't be caught by an unconfigured EDR software. Along with this talk, I'm providing both resources on GitHub and a companion blog with more technical detail. The resources will allow you to run the same simulation we're discussing today. I'll provide a link to both at the end of this talk, and also they're available in my conference Slack channel. So we picked our binary, Chrome. We now need to understand, what should our attack do? What should we simulate? Let's act like a real supply chain malware and use SolarWinds as a blueprint. You can go very in depth and create a piece of malware that mimics all aspects of the SolarWinds attack. And there's a lot of value in that. It was a very successful attack. It ran undetected for about 6 to 9 months, I believe, before it was detected by one of the best security companies in the world. There are awesome blogs out there and resources that will allow you to craft a really similar piece of malware. But you also don't need to go too crazy. And that's something I stress for Purple Team exercises. Keep it simple. At the end of the day, attackers often begin by dropping low detectable malware on machines. But before long, they're using the same tried and true TTPs that we see time and time again. So we'll focus on emulating an adversary that's landed undetected on the network inside a signed binary executable and uses that executable to initiate the attack. So we want to create a realistic but controlled piece of malware as a foil for our detection. How do we build it? Well, first, we want to make sure our malware avoids antivirus and ideally EDR. The best course of action, like I said earlier, is write it yourself. The second best course of action is to use the resources I'm providing in this talk today as a template, and that's why I'm giving the talk. Second, you need to set up a command and control channel, a C2 channel. You can use an off-the-shelf C2 product, but you don't need to. I actually highlighted in my November talk on Purple Team phishing simulation how to use an off-the-shelf C2 in Purple Team exercises. But today, I'm sharing a bare bones C2 that emulates what a C2 does without any of the frills. Why? So you don't need to go through the effort of modifying a C2 to evade detection. Finally, we need to prepare an adversarial execution plan. And this part is up to you, but you don't need to go it alone. Scythe has some phenomenal resources in their community threats repository. Please take a look at them. They're excellent. MITRE also has their adversary emulation library available. If you don't know what an adversarial emulation plan is, if you've never heard that term before, but by the way, you should, because there was a talk earlier today that discussed what one was, but essentially it's a scripted series of steps that can be replayed in a deterministic manner that mimic a real world adversary behavior. You can use this to emulate malicious behavior on your network and to build detections to combat its execution. At a high-level view, our synthetic supply chain malware executes in the following manner. Chrome.exe executes. And execution is disrupted by our modified crypt-based .dll. Crypt-based DLL contains some custom shellcode that's actually our stage 0 dropper, I like to call mic drop. Since mic drop is a C# assembly, the shellcode is prepared using the utility donut. Mic drop performs some situational awareness on the target. Is this our target network? Is this the target user? If these situational awareness answers are yes, then it downloads and executes the stage 1 mic C2 agent. Upon execution, the agent checks into our C2 server, which begins execution of our adversarial emulation plan. One item I want to point out is that Chrome.exe will not execute properly when we hijack execution with crypt-based .dll. And again, that is okay. It's possible to use DLL proxying to make Chrome work while hijacking execution, but it's not necessary for the simulation. The events we are attempting to detect will fire the same either way. So make it easy on yourself. So we spent some time and effort to create a piece of malware that will hopefully be undetected on the network. And like a realistic attack, the dropper and stage malware should evade detection. But what can we detect? TTPs, tactics, techniques, and procedures. How do we do that? The best tool for the job, in my opinion, on Windows networks is Sysmon or System Monitor. If you aren't familiar with Sysmon, you should be. It's one of the most capable logging utilities available for Windows environments, and it's completely free. It's provided as part of the Microsoft sysinternals toolset. And I'm not going to go over it today, but in my blog post, I have a link to an article that the folks at Black Hills Information Security prepared that is a comprehensive guide to all the event codes generated by Sysmon. So definitely take a look at that. To set up Sysmon, simply download the binary and use the -i flag to install a configuration file. And by default, Sysmon doesn't really do all that much, which is why I recommend using the configuration provided by Swift on Security of Twitter fame as a baseline. Again, I have details how to set up Sysmon and install this configuration in my corresponding blog. But one popular question is, and it's the question I had the first time I fired up Sysmon, I started Sysmon, where are my logs? So Sysmon logs are aggregated by Windows Event Viewer, and they're located at Applications and Services Logs, Microsoft, Windows, Sysmon, Operational. Another thing I recommend, before you execute your synthetic supply chain malware, clear the log. This allows you to get a clean view of the events that can be attributed to the malware. Now, in the next few screenshots, I'm going to step through a few highlights of the supply chain malware execution. The first sign that things might be wrong is that Chrome.exe is generating a create remote thread event with a target of Explorer.exe. This would be a really popular adversarial move. Create remote thread migrates execution from a thread from one process to another. Explorer.exe is often the target for abuse as it's a process that's always running on Windows systems. Clearly, this behavior that targets Chrome is not one it should, clearly this behavior that Chrome is engaging in is one that should never really happen. But remember, not all create remote thread events are malicious. Remember, adversaries abuse native Windows functionality. We like native APIs. We like native executables. We like to live off the land. So while this is an event one should monitor, it should be tested at scale to understand what false alerts might be generated on your environment, inside your environment on a regular basis. And I will stress that you have to do that for every one of these steps. Next, we have a series of DNS queries to some suspicious hosts. An adversary isn't going to call their host Kali.host and attacker.host, but they may make calls out to strange domains that have never been seen in your environment, like AVSM cloud that was used in the SolarWinds Sunburst incident. The other strange thing is that these calls are being made by explorer.exe. While web requests can be generated by explorer.exe, how common is this in your environment? And especially, how common is it that web requests are generated by Explorer that have never been seen before? As we continue execution, I actually made this next step a little easy. The adversary decides to use cmd/c to execute commands and fires up the trusty whoami.exe. And we sort of scoff at this, but I'll tell you, I've executed the same on a wide variety of networks without any response at all. So before you scoff, make sure you can detect this. Next up is dir c:/users, again executed by explorer.exe, which is strange. It's clear in this step that the adversary is trying to emulate usernames from the system. And execution continues onward. Several process create events are triggered, and a variety of interesting binaries are all being called by explorer.exe. Binaries that almost no user would execute frequently, let alone all in a short period of time. So it's clear from these steps that the adversary is conducting either situational awareness or reconnaissance on the target network. Sysmon isn't the only useful tool in town, though. While Sysmon is great at detecting Windows event IDs, other tools are more powerful for analyzing network traffic. And the best free tool for the job is Wireshark. Now, you aren't likely going to be running Wireshark on your network 24/7, but Wireshark is a great tool to understand what traffic anomalies might be generated by the simulated supply chain malware. Then we can work on detecting these elsewhere on the network. For example, is this a valid browser? It's an outdated version of Chrome. Maybe the adversary uses an updated version of Chrome, but your company is still locked into using IE6. Now, I'm joking. You're actually on IE8 now. But my main point is look for clues and anomalies that stick out in the network traffic. This is another anomaly, this MS-DOS program string. I made this example really easy as I'm just downloading micdrop.exe. But again, before you scoff, can you detect this? Can you detect it if it's embedded inside an image? Can you detect it if it's base 64 encoded 2 times? Can you detect it if it's XOR encrypted with a passphrase? Start basic and continue to work your way up as you gain confidence in your ability to detect anomalous traffic. And that's it. Where do we go from here? It's sort of a choose your own adventure game. You can take the supply chain framework I provided in this talk, which is available on the links on the slide, to simulate a supply chain attack in a Windows environment using DLL hijacking. The next step is the hardest part, and that's the one part I can't do for you, and that is to build up a realistic adversarial scenario in your environment and work on those detections. And at this point, I will turn it over to any questions I have before I head into Slack.
That is awesome, Mike. Thank you so much. Thank you for the shout out to Scythe. Love that. Didn't know that was coming. And thank you for releasing another C2 that I now have to go test and add to the C2 matrix. So keeping us on our toes as usual. We loved it. We have a couple questions here and we have time right before our next break. So Michael asks, does it make a difference where Process Monitor, in this case, is looking for DLLs if Chrome is installed by a non-admin user?
I don't believe so. So the location of the DLLs to hijack will probably change. I think in Windows 10, you can install software as a regular user and it gets stuffed somewhere in the user's username directory. So yes, it will change the path, but the process to find those will be exactly the same. Just fire up procmon, target chrome.exe, and you'll start to see what DLLs is actually trying to pull off your system.
Awesome. Yeah. And what I added to that, and I mentioned it right before the talk as well, I just want to reiterate that DLL hijacking is one of those procedures, if you will, that spans multiple tactics, right? If that DLL that you're hijacking, you have write access to, which is technically another technique. I think it's weak file system permissions. Don't ask me how I memorize these. So yeah, you have to leverage multiple ones. But if the process is running with the admin and you hijack it, you're going to get privilege escalation. And if the process is going to run, say, on start, or maybe when the user logs in, or when the user double clicks Chrome in this case, then now it's a persistence TTP and not so much a privilege escalation. So it's very useful in multiple ways. So great topic here. And of course, linking it back to the third-party risk, right? The supply chain attack, which you have defined well. Thank you for that. I think nowadays everyone's like, supply chain attack means everything. But excellent. Let me see. I don't think there were any other, would detections that catch activity like DLL hijacking be a similar workflow for getting detections against something like alternate data streams? Or are they too unrelated?
I would say alternate data streams is what happens after the C2 starts up, right? I don't think the MITRE attack definition of alternate data streams is like the data flows within an application. It's network communication, right?
Yeah, I would agree with that. I think the DLL hijacking, one is, an opportunity that can occur on the endpoint, but then also you're dropping the DLL, and that's why you just showed how easy it is to get around signature-based controls by creating your own C2.
Yeah, watch out for your red teams doing this to bypass antivirus. I've noticed a lot of threads, people talking about this, because that window of detection is getting smaller and smaller, which is good. It's a good thing, but this is a new one that people are seeming to abuse.
Yep, agree with that. So thank you so much, Mike.